Then, well, how is this increasing? Well, if I have a doubling of length, how does that affect the number of squares? Well, I have 4 times more squares. If I triple the length and width, I get 9 times or 3 squared more squares. Here I get 2 squared more squares. So relationship then is if I have 1.5 times the length, I'm going to get 1.5 squared, which is 2.25 times more area. Okay, well, let's just check this out. Does this really make sense? So if I have 1.5 times bigger, that's going to be the green square here. Okay, so how many times more area do I have? Well, I know that that's half a square, and that's half a square. So that's going to give me 2 squares. I've doubled the squares here. So this is 1.5, 2 squares, and this square represents 0.25. So yeah, I've got 2.25 times more area. Okay, so I started with 1, now I have 2.25. So my increase is going to be 2.25 times more. And that is the same as 1.5 squared. So this relationship holds true. We're going to generalize this then. So if we increase the side length and width by n, we're going to increase the area by n squared. So if I make it 10 times longer, 10 times wider, I'm going to end up with 100 times more area. Okay, we're going to look at volume later, but let's see how this holds true for other shapes. Well, it doesn't matter that we're talking about squares. Really, it holds true for any shape. So if you take a look at this diagram here, this object, this is double the length, double the width, and this fact is 4 times area. So if I have, this is times 2 this way, okay, and I have times 2 this way, times 2. Well, 2 times 2, I'm going to square this. I'm going to end up with 4 times more area. Same with this one here. If I double the length, so I have times 2 this way. Okay, now although it's not a square, 4 of these is going to fit inside this heart. Okay, and times 2 this way. I'm going to have 4 times more area. Okay, so in general, we increase the length by a factor of n. The area increases factor of n squared. So how does the volume change? Okay, well, if we take a look at unifix cubes, we can see that if we start with 1 cube and double the length, width, and height, what's going to happen? Well, we're going to start with 1 cube, and we're going to double the length, double the width, so we're going to have a square of 4, and instead of having 1 layer high, okay, so having 1 cube, 2 or 4 cubes, right? We're going to have 1 layer of 4 squares, which is 4 cubes. Okay, now this is getting really messy, but okay, you can kind of maybe imagine there's 1 layer of cubes there. I'm going to have now a second layer of cubes. So we're going to go from 1 cube to 8 cubes. Okay, so we went from 1 to 8 times more volume. So when we times by 2 this way, times by 2 this way, and times by 2 this way, we have 2 times 2 times 2, or 8 times, or 2 cubed more volume. Okay, so let's just write that into our table here. We double, we increase the volume by 8 times. Okay, so then I'm just going to get rid of that picture because it's a little bit distracting. It's not the greatest picture. Okay, so we have 8 times more volume. So if we triple the length, width, and height measurements, so if I go from a 1 cube to a 3 by 3 by 3 cube, by what factors did the volume increase? Well, I started with 1 cube, but 3 by 3 by 3 cube is going to end up with 27 cubes. Okay, so we're going to increase by factor of times by 27. Or in other words, I'm going to have 3 times longer, 3 times wider, 3 times deeper, or 27 times more volume. Okay, so if I go to my table here, I'm going to have times by 27. Well, I ended up with 8 because I did 3 times 3, 2 times 2 times 2, or 2 cubed. This is 3 cubed. If I increase by 1.5 times the length, width, and height of a cube, then using my calculator here, I'm going to have 1.5 cubed more volume. So I'm going to have 1.5 cubed more volume, which is 3.375 times more volume. And in general, if I increase the length by a factor of n, I'm going to have n cubed more volume. And again, we're talking about factors, multipliers. Okay, so that's why I haven't given you really a specific starting area or a specific starting volume. This works for all relationships. Okay? So we can try some problems here. So we're going to generalize this relationship. So if we increase the length of measurement of cube, we increase the length measurements, we increase the volume by a factor of n cubed. Okay? And we could do this, so the area increase is going to be by squares of the length, and the volume increase is and again, this is the increase factor, times factor. The volume increase factor is going to be by the length cubed. So I have circles radius 5, and that increase to radius of 10. So I have radius 5, and it increases to radius 10. Okay, so that's double the length, the width, and the height. By what factor does this area change? Well, it looks like I could fit 2 and about 4 times. In fact, it is 4 times because my factor, my length factor increase here is by times 2. So the area increase must be equal to 2 squared, or 4 times more area. Okay, so that's and we can justify that. We can actually see that. And it doesn't matter if the area is a blob. Okay, this blob here, this object is increased by a factor of 16. So how did the length and height change on this object? Well, if I'm squaring, going from length to area, I'm going to square. What happens if I want to go backwards? In this case, I want to go backwards here. So I want to go, what was my length here if I have 16 times more area? Okay, well, I want to figure out the length increase. Well, if I'm going to go backwards from squares, I'm going to square root. Okay. I'll just move that over here so you can see it a little bit better. But yeah, I'm going to square root. And this is a generalization I can use. So if it's 16 times more area, and that, if you actually counted this, you can fit 16 of those inside there, the length change is 4 times. Okay, the length and width change. So I can actually see, yeah, my length, yeah, I can fit 4 of those long here, 4 of those long here. That's going to be a 4 times change. And to get that, I'm going backwards, so I'm going to square root. Okay, so here I have a 5 by 6 rectangle. So I've got 30 centimeters square here. And I'm going to double the area. Well, that's a little bit more than double. I don't know. So I'm going to keep the same dimensions. And I'm going to double the area. So this is 60 centimeters squared. Okay. So I've increased, it's times 2 area. Okay, so what is the length change? Well, if I multiply the area by 2, I need to figure out the length change from here to here. Okay? So my length change is going to be to do with the root of that. So if I doubled the area, I need to root that to get the length change. Which is about 1.41, if I'm not mistaken. So if I doubled this length and width, that's not going to give me 60. It's going to give me 120, isn't it? 10 times 12 is 120. That's too much area. I need something less than double. And the multiplying factor I need is 1.41. So if I were to figure out the length and width of this, it's approximately, now because it's not a nice number, square root 2 is not a nice number, okay, it's going to end up being not a nice decimal, so I'm going to end up with 7.07. That's times 5, and then I'm going to get 8.49. Okay, so approximately, if you multiply those together, 8.49 times 7.07 is approximately, and if you multiply those two numbers together, I'm getting 59.99. So that's approximately 60. Okay, and that's only off because of the rounding involved here. Okay, so the length changes by a factor of 1.5, or the square root of the area change.